6, 95, 99?
109.
109? 109.
Close.
Okay? All right, now take 109, and we want the average of all of those, so divide by 1, 2, 3, 4, 5. Okay? 109 divided by 5.
21.8.
What do you get?
21.8.
21.8. Take the square root of 21.8. 4.67. That's your root mean squared velocity. 4.67.
Guys, the root mean squared. Listen to the word. Root mean squared. You're taking the square root of the mean or average of the squares.
Okay. Then,
The name tells you what to do. You're taking the root of the mean or average of the square value. Hey guys, average those numbers just straight up, not do anything weird to them. Tell us what that is. What's the average?
Just an average, not when they're squared, just an average. Don't square them. 4.2. Okay? What was it the other way? 4.6. So does that correspond with your arrows? The average ends up to the left of your root mean squared, doesn't it?
And the reason why the root mean squared is up to the left, guys, is the process of squaring things emphasizes bigger numbers. Those outliers get weighted even heavier when you square it.
Okay? Now, in some of the formulas that we have, we're going to use that root mean squared. Now, it's a possibility that they might on this test, Mr. Cox, you think, ask them to find the root mean squared? That might be one of the questions. Okay? So make sure that you know how to do that. It's not a hard process. Just make sure that you're familiar with that. Okay? So the kinetic theory over here, we know that kinetic energy is 1/2 mv squared. So we have that V, the V that we're using is the root mean squared. Right? Now, we can take that and we can also find the kinetic energy by taking 3/2 kT. K being Boltzmann's constant and T being Kelvin, whatever the Kelvin temperature is. Here it's, I don't know, 300 for the blue, 1200 for the red. And you can find the kinetic energy of the particles. Now that's the average. Okay? Average kinetic energy of the particles. And if you want internal energy, U, which we're going to talk about in a little bit when we get to thermodynamics, and looking at the effect of U, the internal energy of the system, as we add heat to it or take away heat or do work on the system or let the system do work, it's going to change this value. We'll get to that in a minute. But we've got two formulas here that are going to make use of that. So we have U equals, actually this is kind of a derivation, N, okay, the total energy is going to be the number of molecules that we have, capital N, times our average kinetic energy. That gives us total internal energy. So it says here internal energy of a monatomic ideal gas. So does that make sense? We're getting the average kinetic energy in the sample based on the temperature. Obviously, the higher the temperature, the more internal kinetic energy we're going to have. That's giving us an average. If we want the total internal energy, then we just multiply it by the number of molecules that we have. N, big N. Big N, not the little n, not moles, big N. Now, instead of this, we can take that 3/2 kT and we can plug that in for 1/2 V RMS squared. Yes, ma'am?
Where did the 3/2 kT come from?
3/2 kT. You know where that's derived from?
No.
I don't either. Yeah. I'm sorry. K is Boltzmann's. Okay, so it's that constant. All right.
That was it.
So we're going to take 3/2 kT and we're going to plug that in for 1/2 mv squared since they're the same, right? And when we do that, we get U equals 3/2 n little n moles nRT. Okay? 3/2 little n RT. Mr. Cox, I think, has those on the second page there, where he's got internal energy. Yes, ma'am. I can't hear you, Victoria. Yell at me.
It says U equals N times 3/2
Second page.
I was wondering that same thing.
Yeah, I don't know. Did you mean to remove the K there, Mr. Cox?
Just another way to think about it. So, if,
All right, listen.
where I'm going with that, I'm actually glad you asked the question. If you look, let me see the board.
We're inside here, top of the first page on the back. Okay? Top of the first page in the back, we're looking at the formula derivation at the top where it says internal energy. Mr. Cox likes the board.
Okay, U equals 3/2 kT. If U is 3/2 kT, and we remember that K is R over NA. So I can write 3/2 R over NA times T. Excuse me, I left out my big N here. If I bring my big N down, what is big N divided by NA? Little n, Avogadro's number. So in the, down below it says complete the formula for U below. Well, U equals little n times 3/2 RT. Or you'll probably see it 3/2 nRT more often. That's why I wrote that way.
We okay there? All right. Now, if you look back on the front, okay, the kinetic molecular theory. We're just under the first bit there. You see where it says kinetic molecular theory? All collisions are what? Elastic. Listen, remember that elastic, they hit and bounce off. It's like a rubber ball. If it's inelastic, they hit and stick, don't they? You should remember that from your momentum talk this morning. Okay? This means that energy is what? Is or is not? Is conserved. If it's perfectly elastic, energy is conserved. Right? Just a little bump for today when we did momentum. If you're talking about collisions, what do you want to use? Law of conservation of momentum. Okay? Because it works for everything. All right, back to this. Conserved in the collisions between gas particles. The spacing between the particles is large or small compared to the size of the particles themselves? Large. Spacing's large compared to the particles themselves, which is small. Individual particles move at random, but the particles as a whole obey Newton's laws of motion. And the last dot, there's no forces between the gas molecules except those occurring during collisions. Meaning there's no electrical forces, nothing like that. Okay? There are no forces between gas molecules except those occurring during the collisions. So those are the basic postulates occurred in the kinetic molecular theory. I think we got everything else.
The answer to the 3/2 KT is a derivation, a one-page derivation under the kinetic theory in their book.
Okay, Mr. Miller said in your book on page 411, if you want to write it down, where Victoria asked the question, was it this one, 3/2 NRT?
The 3/2 KT.
3/2 KT. The derivation of 3/2 KT is on page 411 of your book, if you want to go look at that.
And it's based on conservation of momentum.
Based on conservation of momentum. Thank you. Okay? Page 411. You don't necessarily have to look at it now, but if you want to go back and look at it, just jot the page number down on your sheet here. Okay? If you look down at the bottom, we talked about those formulas there underneath the speed of the gas molecule. The three types of speed. V RMS, we showed where that was on the graph. V most probable, we showed that, and also V average. So we're complete on the front. Mr. Cox, do you want to add anything to that?
No, good.
Okay?
On the back, one other thing I want to mention before we start working some practice problems. When we wrote down under complete the formula for U below, and we said U equals 3/2 N little n RT, what I have boxed on the board up there, what comes down stands up and overhead up there. Okay? Look at that formula. There's a major implication that comes right out of that formula. If you're talking about the internal energy in a gas sample, there is no change in internal energy unless you have a change in temperature. If it's a closed sample, unless there's a change in temperature, there's no change in internal energy. That's a major consequence. There's space to write down your sheet. Okay, guys, what we want you to do right now, on the practice test we gave you, problems 1 through 14, omit number 9. Okay, we're going to give you about 20 minutes to work on that right now while we walk around and help you.
Answers on the back of that practice test, so I'm sure you found that, but if you want to go look at the answers, it is on the back. Okay, we're going to look at thermodynamics now. We're going to spend a little bit of time on these laws, and in particular on the graphs, because you're going to see one or two of those on the AP exam, and they're easy points if you know how to work with them. Okay, the first law that we want to work with is the 0th law of thermodynamics. I don't know why it's the 0th. Do you know?
They forgot it.
Is that true?
Yeah, they said this is the first. They said, wait a minute, this is even more basic than the first.
Okay.
No, you can't rename.
You're lying.
Well, no, what's the first? You gotta
Okay.
say the first.
All right, so it's the 0th. You were right. Okay, so it's the 0th law. And basically what the 0th law says is there's going to be no heat transfer between two bodies of the same temperature. Doesn't really take an advanced degree to figure that one out. Okay? You've got two things that are the same temperature. Remember, temperature is really a measure of molecular movement. The faster the movement, the higher the temperature. So if two bodies have the same temperature, there's no net transfer of heat between the two. And it even goes farther to say that if body A is in thermal equilibrium with body C, and if body B is in thermal equilibrium with body C, then A and B must be the same temperature. They must be in thermal equilibrium with each other. And that kind of makes sense too, doesn't it? If A is equal to C and B is equal to C, then A and B must be equal. That's the 0th law. So not too complicated there. Maybe we'll get a question over that on the AP exam. That'd be nice, wouldn't it? But just remember that there's no heat transfer between the two. Okay? All right, first law down here. You guys are funny sometimes from our aspects, all three of us, because you do this so much. So you go back and forth in between classes and you're beep, 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 beep. Mr. Nelson did this, Mr. Cox did this, Mr. Miller did this, okay? Well, when we did this formula in my class, for those of you in my class, we looked down here to the first law, which is going to relate work, heat input, and internal energy of the sample together. and we did this formula. Delta U, the change in the internal energy of the system, is going to be equal to the heat that we put into the system minus the work that is done either on or by the system. We had a minus sign. The rest of you guys, if you were in Mr. Cox's class or Mr. Miller's class, there was a plus. Okay? And so what I told mine, regardless of how you see the formula, make this work. Okay? Not work as in this work, but make it work. If you're intelligent, make it work. Okay? So, what you're going to see on the AP exam, on that formula sheet, if you looked at it, that's going to be a plus. Your book has a minus. Okay? But your formula sheet on the AP exam is going to be a plus, so we need to evaluate it that way. Delta U, change in internal energy, equals Q, heat input, plus W. Now, the important thing is for us to be able to evaluate the signs that go with the, not so much the Q, but definitely the W. So if we take heat, there she is. I knew she'd come. Okay? All right. We've got the W, internal energy. If I input heat, okay? If I put heat into the container, what's going to happen to the internal energy inside the container? It's going to go up. That's a no-brainer, isn't it? So if this Q, it doesn't matter what that back sign is. If Q is positive, that's going up. If Q is negative, that's going down. If I'm removing heat, maybe I've taken my container and I've set it down in an ice bath. Heat's going to leave the container. Right? Okay? And remember transfer of heat. While we're talking about it, just so we can say this or something, where does heat move? From hot to cold or cold to hot? Hot to cold. Okay, think about this. Okay, I shared this with my classes. In my garage, I've got a refrigerator. Garage gets hot in the summer now. If I open up my refrigerator and energy moves from cold to hot, what's going to happen to the refrigerator when I open it up? It's going to get colder. If energy moves from cold to hot, when I open up my refrigerator, it's going to get colder. Is that going to happen? No. So the energy must go from hot to cold. So when the energy leaves the hot garage and goes towards the cold refrigerator,